Okay, this is for Physics 5B. It's July 31st, 2020, like 8:08 p.m. at night on a Friday night. So this is what's up now on Canvas. The new equations are up for Chapter 21, and so they look like, wherever I have them, here they are. So here you've got the equations for Chapter 21. Also up on Canvas is the newest PowerPoint presentation. That's this one right here that we'll be looking at. And then also up on Canvas is going to be the new, so online 6 is up now too, and that's going to look like this right here. So there's online 6, there's the new homework, which is Chapter 21, due August 4th, which is the day of our second exam. Okay, so let's start off with the PowerPoint, and we're Chapter 21.1, Resistors in Series and Parallel. In a series circuit, the electrons have to flow through all resistors. They have no choice. So electrons over here has to go through that one, and then that one, and then that one, and then that one. There's no choice. Let us try a model to help us understand. You are an electron. You are in Sam's Club or Costco late at night. You just want to pay for your stuff and get on your way home. There is only one checkout line, so it's so late they only have one open. So you have to wait in this line. So you got one resistance for you getting out of the store. This is a resistance you face trying to get out of the store, just like an electron wants to get to the positive side of the battery. You get through the line and you are hoping that you are in a simple circuit, which would just be one resistor. But then there is another line of people showing some guy at the door their receipts. Now they do this in Walmart now too, so it's not just Sam's Club and Costco. This is a second resistance you have to pass through, so you have found yourself in a series circuit with two resistances in your way. Then maybe you get out to the parking lot and there was a fender bender or something, and the cops are there, and everybody's got to stand in line to talk to the cops to tell them what they saw. So you got to stand there and wait till you can tell the cops you didn't see anything. So then you can be on your way. That'd be a third resistance for you getting home. Okay, so the electron's home is the positive side of the battery. Okay, so in a series circuit, the one thing that happens is the voltages have to add up. Okay, so whatever voltage you have from the battery has to equal this voltage plus this voltage plus this voltage. If this is 20 volts, this is 5 volts, and this is 5 volts, and this better be 10 volts. They got to add up to 20. So the voltages add up in a series circuit. We know from Ohm's law that voltage equals I times R. So the voltage across R1 would be I R1, the voltage across 2 would be I R2, the voltage across 3 would be I R3, all the way up to however many resistors you have. Okay, so you can take out the I. The current's the same everywhere. Whatever current you measure here, you're going to measure the same current there, there, and there. It's the same current everywhere. Okay, so we can factor out the I. So you've got R1 plus R2 plus R3, however many R's you have. So we would say that V battery, the voltage from the battery, equals the current running through the circuits times R series, and R series would be equal to these guys added together. So that's a series circuit. Now, parallel circuit. Okay, the parallel circuit, the electrons have a choice. They have two pathways to get from the negative side of the battery to the positive side of the battery. Another model involving grocery shopping. You are on Raley's or Safeway or another similar establishment. You just want to pay and get home. There is one line open. This looks like a simple circuit. There's one resistance you have to go through. And then another store employee walks up and opens another line. Now you have a choice. You can get on your way faster. Everybody can spread out. Everybody gets out of the store faster. It's like the resistance facing you has been reduced. You pay for your stuff in this checkout line, while other people representing other electrons pay for their groceries in the other checkout line. And you could open up a third checkout line, a fourth checkout line. So to the electrons, that's like you're reducing the resistance if you keep adding them in parallel. Add them in series, you're increasing the resistance. Add them in parallel, you're reducing the resistance. So resistors in series and parallel. Now in this case, the currents are different. The voltage is going to be the same. It's the same voltage because this battery is holding all this at like say 10 volts and all this is 0 volts or whatever the voltage difference is going to be. You can have the same voltage across this guy as across this guy as across this guy, or however many you have. So we can add up the currents. The total current has to add up. I1 plus I2 plus I3 has to add up to the current coming from the battery. So the current equals V over R. So now what I do is say, well, the current going through R1 is V over R1. The current through R2 is V over R2 all the way up. Factor out the V's. I factor out the V. You got I equals V times 1 over R1 plus 1 over R2 plus 1 over R3 all the way up to 1 over Rn. And then I then equals V over R parallel, or 1 over R parallel equals 1 over R1 plus 1 over R2, whatever, all the way up. If you only have two resistors, you can say R parallel equals R1 times R2 divided by R1 plus R2. You can show that. So if you only have two, you can take that little easy step. Okay, so I think we can do some of these problems we have here. Okay, this is what you have, except you don't have you don't have this right here. Okay, but I've got it here for you. What is the resistance of a 100 ohm, a 2.5 k ohm, and a 4 k ohm resistor connected in series and in parallel? Well, in series, we just add them together. Okay, 100 plus 2.5 k plus 4 k equals 6.60 kiloohms. Now in parallel, we got to do the 1 over thing. So you've got 1 over 100 plus 1 over 2500 plus 1 over 4000, and then what do you get? You get this number. Okay, but we got to take 1 over that number. Okay, so if you take 1 over that number, so R parallel, there should be a break right there. So R parallel, did I even put one in there? Nope, it did that. Okay, so R parallel, this is a separate thing. Right here, this is separate here. I don't know why I can't get it to work. All right, so anyway, R parallel then, this is 1 over parallel. 1 over R parallel is this. So R parallel, take 1 over both sides. We take 1 over the 1.6 whatever, and then ohms goes to the top. And we get 93.9 ohms. So 93.9 ohms if they're in parallel. So look at the difference. If you add them in series, you get this huge resistance. If you put them in parallel, you get this very small resistance. So you're ready to do this one yet? This one doesn't seem like it belongs here. Wait, let me look at this. Okay, yeah, this is just a series problem, just a little bit more complicated. So your car's 30 watt headlight and 2.4 k watt starter are ordinarily connected in parallel in a 12 volt system. What power would one headlight and one starter consume if connected in series to a 12 volt battery? Okay, neglect any other resistance in the circuit. Okay, so we just figure out how do we find the resistance and we have the power and the voltage. We've got the 12 volt system, we've got the wattage. So you solve for R, V squared over P. So for the headlight, you'd have your 12 volts divided by your 30 watts, 12 volts squared divided by your 30 watts. Your resistance for your headlight would be 4.80 ohms. For your starter, still 12 volts, but now you got the 2.4 k watts. So you square your 12 volts divided by 2.4 kilowatts, and you get 0.006 ohms. So that's either 0.06 ohms. That'd be the resistance of your starter. Now it says they're in series. They're normally in parallel, but if they were in series, I think they're always in parallel, but this is just a suppose, pretend like. So our total equals our headlight plus our starter, so that's going to be equal these two added together, but it's going to be, so you can see that plus that's going to be 4.86 ohms. So now to figure out what the power would be, you just go your 12 volts doesn't change, but now you got your resistance. We're going back to this equation because we know the total resistance. We'd have 29.6 watts. Okay. All right, so given a 12 volt battery and 6 ohms and 32 ohm resistors, find the current for the power and power for each one connected in series. Repeat when they're connected in parallel. Series, we add them together, so this would be 38 ohms. The current would then be 12 volts that we were given there. I didn't find the power. Okay, the power, you just multiply them together. So you go 12 volts times 38 ohms, okay? So for the current, you just divide them, what you get the resistance, divide them, and the same thing, you just find what the resistance is, 5.05 ohms. So then the current would be 12 volts divided by 5.05 ohms, 2.38 amps. And then for the power, you just multiply them. So this guy's power here, I'll just give you what it would be. It'd be 12 would be 12 times. Current is 12 volts. Wait a second. No. Okay, we'll just go the current. So 316 milliamps, 316 milliamps times voltage 12. So I'm getting 3.792, 3.79 watts for this one. Okay, this one here, again, just go current times voltage. So P for this one, P for this one will be 2.38 amps times 12 volts equals 28.56, 28.6 watts. Okay, so that's how you would do the power. You just multiply them. Okay. Oh, we can't do this one yet. Okay, so going back to PowerPoint. Okay, electromotive force and terminal voltage. Voltage sources are able to create voltage differences. So here you got a bunch of examples of voltage sources, things that are able to create voltage differences. And it's voltage differences that gets current to flow. Windmills, there's a dam. They use a Russian dam. I don't know why they couldn't use Folsom or something like that. Some batteries, and I guess these are solar cells or something. Yeah, solar panels really are. I can see them now. All right, voltage sources are able to create voltage differences. When a voltage source is connected to a resistance, the electric field generated by the voltage source pushes electrons through the circuit. The term electromagnetic force, EMF, is used to describe this voltage difference. So EMF, electromotive force, is not a force. It's a voltage. It's a voltage. It's a difference in voltage. It's a potential difference. EMF is not a force, but a voltage. So all voltage sources have some sort of internal resistance. When current flows, voltage is dropped, energy is lost across this internal resistance. The voltmeter has a very high resistance, so when one is connected across a battery, very little current flows. Therefore, we are essentially measuring the EMF of the voltage source. So you got your battery, you got your terminal voltage. This is what you get out here. Okay, this is what you're sending the voltage to the rest of the circuit. But you get a current. The current is going to go across the internal resistance. You can't help it. You don't want a internal resistance, but it's going to be there. So what happens is, whatever this guy would be, you get less of it because some of it dropped across this internal resistor here. So let's say that it's 10 volts is what you expect to get out of it, but you lose 1 volt here. You're only going to have 9 volts out here because you lost a volt right there from your 10 volts. Okay, the voltmeter. Okay, so when a smaller resistance is connected, more current flows and it is more of a loss to the internal resistance. So yeah, the smaller the load, we call it, the load out here is, then the greater the current's going to flow. Well, that current's going to flow through that guy, and then V equals I times R. So even though R, whatever R is, you're going to have that times V, that times I. That's going to be your voltage drop. So the voltage you actually see at the terminal is equal to the EMF, the electromotive force, this guy here, minus the current times this internal resistance. That's what you're going to get out of it finally, because you're going to lose some of it right here. Okay, electromotive force, terminal voltage. The voltage we actually get out of the battery after the loss to the internal resistance is called the terminal voltage. The terminal voltage depends on the current drawn from the battery, so therefore it depends on the resistance connected to the battery, referred to as the load we put on the battery. The value of the internal resistance can change depending on the number of factors, including the age of the battery. If you've got one of those rechargeable batteries, the more you recharge them, the higher the internal resistance gets. Gets too high, then it's a useless battery basically. And other things too, like someplace I read it could depend on which direction the current's going through, and it could change based on the amount of current too. So it's not an ohmic value. Like say an ohmic, it's not ohmic. Okay, we're at Kirchhoff's. Okay, so let's go back. I think we can do some more problems now. All right, so what is the terminal voltage of a large 1.54 volt carbon zinc dry cell used in the physics lab to supply 2 amps to a circuit if the cell's internal resistance is 0.100 ohms? Okay, so The terminal voltage equals the EMF minus the current times the internal resistance. We're expecting to get 1.54 volt. Well, what is it? Okay, so yeah, EMF is the 1.5. We're looking for the terminal voltage. This is the EMF, 1.54 volts. So the EMF, the E there, is 1.54 volts, but minus what we lose across the internal resistance. The internal resistance is 0.100 ohms. We got 2 amps. So you got your 2 amps times your 1.00 ohms. Obviously, that's going to be 0.2 volts. So you lose 0.2 volts. So instead of getting the 1.54 volts EMF, you're going to get 1.34 volts out because you lost 0.2 volts across the internal resistance. How much electrical power does the cell produce? Well, power equals current times your, so it should produce 3.08 watts. Okay. What power gets to the load? Okay, so the power that's going to get to the load is going to be equal to the normal, the 3.08 watts. This is what is supplied. See, it says how much electrical power does the cell produce. So we've got it. That's including the power that we lost across the internal resistance. So in other words, it's the total power. So we take the total 2 amps that we get out of it times the total voltage we should be getting, the EMF, the power it does, the voltage it does supply. Okay, so there, that's this guy. That's the total that it does supply. But how much is the power we lost across the internal resistor? So we got to go 3.08 times, well, we had 2 amps go through that internal resistance. We got to square that, multiply the times resistance. So 2.68 watts. So we lost quite a bit of power inside of that battery. That's is useless to us. Okay, now in this case, this is charging a automobile battery. So instead of taking energy out, we are putting energy in. Okay, that means the current is going in the opposite direction. Okay, so that means where we had the, for example, here you got the minus sign, now we got the plus sign. Okay, so what is the internal resistance of an automobile battery that has an EMF of 22 volts at a terminal voltage of 24 volts? In other words, there's more voltage, we're putting more voltage in than the EMF because we're charging it. We're giving it energy, okay? While the current, and we're putting in 10 amps to charge it. So now since the current goes in the opposite direction, we actually have the EMF plus, it's also getting whatever we put across that internal resistance, okay? This is the terminal voltage. We're putting that voltage in. We're not taking that voltage out. We're putting it in to charge the battery back up. So the internal resistance is going to be, just solve for internal resistance. We got 24 volts minus 22 volts divided by 10 amps, or should be a, okay, it's going to, well, that's right, you don't have it. So it's supposed to be omega there. Okay. You don't have it, this filled in, but that's supposed to be an omega there. Okay, ready to do this. Alright, this one, hell, I'm not gonna ask anything like this on like that. Maybe later I'll come back and do this, but let's skip that one for now. I'm already, so I'm already close, we're over 20 minutes on this. Okay, so what is this? 20, okay, galvanometer. So let's continue on. Let's go back to the PowerPoint because we're not to this point yet. Oh, we got to talk about Kirchhoff's rules. Okay, Kirchhoff's rules could be a nightmare. I mean, just take a look what your textbook have on it. Textbook, Kirchhoff's rules. It's horrible. Does your book have a? See this. This is even an easy one. But you got this current loops and you got these voltage loop. I mean, you got these current nodes and these voltage loops, and you get this. Look at this algebra. Look at that. So the physics is up here. The physics is done someplace around here. And then the rest of this is algebra. This isn't physics anymore. So this is why we're not going to go in depth on Kirchhoff. But here's what you need to know about Kirchhoff. Okay, Kirchhoff's first rule, the junction rule. The sum of all the currents entering a junction must equal the sum of all the currents leaving the junction. So here you got 11 amps coming in, you got 7 amps going this way. Well, you better have 7 amps going that way. You can't build up current in here. It's got to, whatever goes in must come out somehow. Okay, that's conservation of charge. The other one, Kirchhoff's second rule, the loop rule. The algebraic sum of the changes of potential around any closed circuit path loop must be 0. Okay, so we got 18, and then so right now this is 0, this is 18. Okay, well, we got to drop 18 volts across the circuit, so we drop 1 volt there. Then we went 17 to 5, so we must have dropped 12 volts there. See, that's 0.5 ohms, that's 6 ohms, so we dropped more voltage there. Then we went from 5 volts down to 0 volts, and now so everything's good. So these voltage drops have to sum up to the same number as this guy here. So those are two conceptual ideas you got to understand about Kirchhoff's. We're not going to mess with the algebra. Okay, now we're into DC voltmeters and ammeters. This is an analog. It's also called a galvanometer, and basically you put the current through there, and you put a voltage through there. It causes this little coil to to basically turn a little bit, and that turning of that coil, because of its reaction to the magnetic field, causes this needle to jump up and tell you what voltage you put across there. This is a digital voltmeter, so we would have been using both of these in the lab. Okay, now the galvanometer, we're going to make it try to see how we make a voltmeter and ammeter out of a galvanometer. So basically a galvanometer is more or less just a coil. This kind of represents the coil. This is the resistance of the coil. So this is the whole thing, okay? This is a coil that has this resistance, little r. This is very small resistance normally. We can hook this coil, oh boy. This is a bad sense. Basically, we can hook this coil up to make electrical measurements. We can hook this, so we can measure, for example, both voltage and current with that coil. The symbol for the galvanometer is shown to the right. R represents the resistance of the coil. So what this represents is a coil, and this is the resistance of the coil. The coil reacts to current, reacts to voltage, and basically it can cause by changing a magnetic field, it can cause a needle to move, and we put that needle on a scale like this, and it tells us what current's going through there, what voltage is across the galvanometer. Okay, now if we want to set up the galvanometer as a voltmeter, the diagram at right shows how to use a galvanometer as a voltmeter. So whatever we're measuring is down here, and this is in parallel with it. Okay, this is in parallel with what we have down here. So we can have a battery here, we can have a resistor here, whatever. But see, whatever's here, whatever voltage is here, this has to add up to that voltage. Okay, we don't have the little r here. It's implied. It's there. This little r here, the resistance of the coil, is there. Okay, that's the galvanometer. Little r is not shown, but it is assumed to be there. Are the internal resistance. Okay, little r is not shown. I'm tired. That's why I just did this like about an hour ago, or probably an hour and a half ago. Little r is not shown, but it is assumed to be there, and the internal resistance. Okay. Maybe I'm supposed to be I don't know. As the internal resistance of the galvanometer. It's the internal resistance of the galvanometer. It's not shown. Too much current can damage the coil, so a large resistance is placed in series. That should be in series, not is series. In series with the coil to limit the current. Okay, this is a big resistance because too much current can damage this guy. Current can go down here, okay, but we got to limit how much goes up this way, so we put a big resistor in there. Suppose you want to design a voltmeter that can measure a voltage V, but can have no more than current I pass through the coil with the resistance of little r. So in other words, we know what voltage up to we want to measure. We know the most current we can let pass through without damaging the coil, and we know what the resistance of the coil is going to be. What should be the large resistance R be? Okay, the drawing on the right is in parallel with the resistor or battery which to measure. The thing we want to measure is down here. So current comes in like this. Most of it goes this way, but some of it goes this way. Okay, big resistor compared to whatever this resistance is. So the voltage we want to measure is going to equal these two voltages here. So we got voltage across the big resistor, the big R here. Then you got voltage that's dropped across the little resistance of the galvanometer. Okay, and so we solve for big R. So you take big R to one side. That's going to mean that we've got the voltage that we want to measure minus the voltage that's dropped across the galvanometer. Solve for big R. It's going to be the voltage we want to measure minus the voltage drop across the galvanometer, which is IGR, divided by IG. IG we have to divide through by IG. So suppose we want to measure up to 10 volts. The resistance of our coil is 25 ohms, and if any current above 50 microamps goes through the coil, we damage the coil. So what R need to be? What R do we need? I need to not be half asleep when I write this. What R do we need? What R is needed? Anyway, I'm going to leave it like this. I'll just get on. Okay, R, so there's our equation we just got up here. Got your 10 volts minus your 50 microamps times 25 ohms divided by 50 microamps. We get this huge number, which these only have two significant digits, but I'm going to write as 3 here. 200 k ohms. So we need a 200 k ohm, 200,000 ohm resistor. Now, we could have forgotten about this term here. 50 microamps times 25 ohms is an incredibly small number. Okay, so what 10 volts, that's why we get this basically this minus this is practically 10 volts. It's like maybe 9.9998 volts. So this actually could be discarded. And then you got the 50 microamps on the bottom, so you get your 200 k ohms. And okay, that was it, because I got tired. I wanted to get this done with. It's already 8:36. I've been working on stuff till noon. I mean, noon is when I started working on stuff. All right. So now we can finish off over here. Where are we? Yeah. Find the resistance that must be placed in series with a 25 ohm galvanometer having a 50 micro. Oh boy, this is the one we just did, isn't it? Find the resistance that must be placed in series. This is the big R with a 25 ohm galvanometer having 50 microamp sensitivity. Oh, but we got a different voltage scale. Okay. So we are given 25 ohms, and we want to measure up to 0.100 volts, and the current is 50 microamps. Anything above that wrecks the coil. Since resistors are in series, the total resistance for the voltmeter is found by you would add them all together. We only have 2 here. So R total equals big R plus little r. Okay, that's going to equal to V over I, because R total is the total voltage times the total current that goes through there. So that R is going to, they're doing it a slightly different way than the way I did it before, but we can use both ways. All right, so anyway, we've got the resistance across the big resistor. They're ignoring the, okay, minus R. So anyway, I should have done this the way I did it. So you got your 10, so it ends up the same, okay, because they're ignoring that other term I told you could ignore. The other term would be the 50 microamps times the 25 ohms. So you just ignore that. You're ignoring that other term. Or they, oh, maybe they got this is weird. I'm not completely sure what the book is doing. You should get the same answer if you use the equation I did. Okay, you should get the same answer. What's this? Okay, this is for making the galvanometer into an ammeter. I didn't get that far tonight. That's the very next thing in your textbook. See, we did this. We did the voltmeter, and then the next thing is the ammeter, but I'm getting tired. So we're going to leave it there tonight. I'm trying to have the rest up tomorrow. We're not going to spend any time with null measurements. We don't have time. We need to do DC circuits containing resistors and capacitors. Okay, and then hold on. Okay, I think that's just about everything. So this will be it for exam 2, I guess. And so I'll try to have another video up tomorrow. I'm probably going to have videos up for the rest of the chapters, maybe even before exam 2 on Tuesday. But we'll leave it as this for exam 2. And then homework number 5 are these problems here. Worksheet is so this is your worksheet. Where did I get this from? Well, I have both of them open? I guess I have both of them open. Alright, so this is the one where nothing's filled in yet. So we didn't get to this one here, 47, and then we didn't get to these at all. Okay, we're almost on this one here. Okay, so that's everything. Again, I'll try to schedule for, I guess, noon on Monday a Zoom session. And okay, I can't think of anything. I'm tired right now. If I think of anything, I'll put it on that blast email I'll send out. So good night.